equations based on what you are given in the equation in the problem, right? So power, like if you think about the concept of energy in this case, so what was the relationship between power and energy? Can someone help me? Like, what is
power was the time rate of change of energy.
Perfect. So we said power was the time rate, the rate of change in the energy, right? So this was the basic equation between the power and the energy. So this time now I can like by using basically these equations, it really depends on the context, but I can use any of them. Like, let's say I will be just using this guy here. This I will be saying this will be equal to L times I times di over dt, so that I have now some common components here between this in this power calculation. So in this case, now if you focus on this part, both are divided by dt. I can simply cancel those over dt terms. So I will be having d omega equals to L times I times di, right? So this will be a very simple energy relationship. So in this case, I can just take the integral of both sides and then I can calculate the energy stored in this inductor, right? So that will be very easy. Let me use a different color so that we can separate things out. So let's say we will be taking the integral. For the left-hand side, this is an integral with respect to d omega, like this energy. So that will start from the initial energy. I can just say maybe omega 0, which is generally 0, by the way. And then let's say, so that will be v of t, right? Omega of t, right? So it will be the power at any time. And then for the right-hand side, that is just an integral with respect to di. This L here does not depend on integration constant. I can just take it out. But for the bonds, I should say this is an integral which depends on di. So this lower bound will be I t0, and then this upper bound will be I of t, right? Is there any problem? But again, just not to confuse ourselves, I will be changing this parameters inside these integrals so that I can get rid of this. But also, I think just for clarity, we will be saying assume. So let's say let I t0 equals to 0. So there is no initial current in this inductor, which means that if there is no initial current, there cannot be any energy, so that V0 will be also 0. This is just an assumption for this case, but of course, this formulation here will allow us to solve this for a non-zero initial condition as well, so that is not a big problem for us. So I will be updating this equation. I will be saying this is from 0 to omega. So let's say this is just dx. I'm changing the variable name so that we're not confused. I will take that L out. So that will be from 0 to I of t, it doesn't matter. And then here we will be having y times dy. Again, I replaced i's with y's so that I don't confuse myself when I plug in those, i's back into this calculation. Okay, so what is the integral now? So this part, what is the integral of dx? It will be just x. So I will put that v in, so that will be, for the left-hand side, I will be only having omega t, right? So what is the integral of y dy?
Y squared over 2.
Y squared over 2, so that will be 1 over 2 times y squared, right? And then I need to evaluate this at I and 0, and then of course I should multiply this with L. So let's try to do this calculation. So that will be omega t, which is the energy stored in an inductor, is equal to 1 over 2 times L times I squared. Because this, if I put the 0 in, that will be 0, it doesn't matter. So this is our energy calculation for an inductor. So this is energy stored in an inductor, right? And also, this is the power. This is generic for inductor, resistor, and capacitor. It really doesn't matter a lot. But now we have a simplified solution for the energy stored in an inductor. Basically, it will be 1/2 times inductance times the square root of the current, right? And the unit of this energy here will be again joules. What was the unit of power here? Unit of power? Exactly, that will be watts. Right? Please be very careful, like pay special attention to units. Sometimes you will be giving like microjoules, millijoules, microamperes, like milliamperes. So you should be knowing how to convert those units to base units so that you can make things right in your calculation. So that is something very important. Okay, so let's do a simple example where we will be applying all these things, and then most of those things will be much more meaningful. So let's say we have an example here. I will be drawing a very simple circuit. So this circuit has a current source, which doesn't look in a good shape. I don't know why it automatically did this, but let's do this. We have an independent current source, which is just pumping current into an inductor here. Okay, so this inductor is, so let's say this is V, the voltage drop on this inductor, and this is 2 millihenries, where you should immediately, like there should be lights flashing in your mind, like whenever you see that milli, you should get that warning. Right? We need a unit conversion. That will be 2 times 10 to the minus 3 henries. Right? Please, like whenever you see those kind of changes, just immediately you should have lights flashing in your mind, like warning message, so that you will be careful about the units. And then let's say this is IG, which is the current we are pumping into the system. And that IG is a function, basically. So that IG is 0 before t is equal to 0. So it's like we turn it on right at t is equal to 0. And then at after t is equal to 0, that would be 5 times e to the minus 200t minus 5 times e to the minus 800t amperes after t is equal to 0. So that is just a graph. That is just a function of the current we are pumping. And then now we have like this question has a lot of subparts, but let's do them one by one. I can't really follow. I won't be able to write them all and solve. So it says, what is the initial voltage at t is equal to 0? What is the initial voltage across the terminals of that inductor? Is there any volunteer to help me? Volunteers? Can you hear me?
Yes, we can.
Okay, then we don't have a, okay, I will do this one. It's very simple. So we are asked to calculate the initial current initial voltage on the inductor. And we know the initial current we are pumping into that inductor, right? So what I should do is I will just calculate V of t, which is valid, by using which I can calculate voltage at any time. And then I will just calculate it at t is equal to t0, basically t is equal to 0, and you will get, hopefully we will get the result. So, so what I'm going to do is, let's see that equation as well. So we know Vt is L times EI over dt, right? So that is something we know. And then I will just put in the numbers. L is 2 millihenries, which is 2 times 10 to the minus 3 henries. And then what is di over dt? So this is I. After before t is equal to 0, I don't even need to calculate anything. It's just 0. But after t is equal to 0 here, what is the derivative of this thing? So I will just basically calculate the derivative here. So that will be minus, so then minus 2,200, no, minus 200 will be just a multiplication coefficient. So that will be minus 1,000 times minus 200t, I hope, right? If that is correct. And then we have this right-hand side where we have minus 5 times e to the minus 800t. So that will be plus 4,000, I think, in this case. 4,000 times e to the 800t. Please double check my calculations. Does it look okay up to now?
Yes, I think.
Right? Okay. And then now Vt is, I can just multiply everything with this coefficient here. So that will be, it's easier than I planned. So that will be just minus 2 times e to the minus 200t plus, is it going to be 8 times e to the minus 800t, right? So that is in the units of volts now. So now I have the equation for the voltage, and what I need is only the result of this at t is equal to 0. So what is V0? So that will be 1. So we will have minus 2 here, and then that will be 1. So that will be 8. So this will be 6 volts, right? This is the solution for the first part of this question. Okay, so the second part says, part B says, what is T star, let's say, when T star is 0? So basically it says, when does the voltage reach to 0? Do you all understand the question?
Infinity.
Atan, can you say again?
Infinity.
Why did you say infinity?
When it goes to infinity, the e to the power of t function goes to 0. So both of them will be 0.
Okay, but can there be other solutions, like other finite time solutions for this?
We can find it from the equation, maybe.
Equation what?
Uh,
This one?
V of t, yeah.
Yes, so how do we find? So basically, let's say we have a given function. How do we find the time instant when it becomes 0? Like we are basically trying to calculate the zero crossing of the function. How do we do this?
Should we take derivative?
And the derivative, yeah.
Perfect. You take derivative of it, equate it to 0, and so that will give you the times, like when is it asking 0 crossing? Yes. Yes. So you take it so just to find. No, wait a second. I think is there a problem with this question?
ln4 over 600.
I will just try to. Okay, sorry, we don't need to take derivative. Yeah. Let me just look at the solution, just to read the solution. Calculate the time instant when voltage reaches 0. Okay, sorry. This is my mistake. We don't really need to go ahead and take the derivative. It's when you're trying to calculate the maximum or minimum values, right? So whenever you want to find local maximums or local minimums, or like global ones, it doesn't matter. You take derivative and equate to 0. But this question is simpler than we thought. It's just asking when this equation becomes zero. So basically, I will just equate it to zero, right? So I will say we t star plus 8 times e to the minus 800 t star is equal to 0. So I just need to calculate that t star. Is it? I think that should be the answer, and we can calculate. We can compare our results with the results I have here. Is it clear for everyone? Like, it's not asking the maximum or minimum, the time of maximum or minimum. It's just asking the time when it becomes 0. So I can just equate it to 0 and calculate that time very easily. So here I can take this to the right-hand side. So that will be like 8 times e to the minus 800 t star is equal to 2 times e to the minus 200 t star, right? And then that will be just 4. So if I divide both sides with e to the minus 200 t star, so that will be something like this, I hope. So that will be 1 over 4. Is this going okay up to now?
Yeah, I think so.
Yes.
Okay. So then this division will be just a subtraction of the powers. So that will be e to the minus 600 t star, which is equal to 0.25, right? So that is just how we go. And then to calculate t star, I need to calculate ln of these numbers, right? So that will be, if I take ln of both sides, so this left-hand side will be minus 600 times t star. And then this right-hand side will be ln of 0.25, which you should calculate. Can someone calculate this number? And then t star is just ln of 0.25 divided by minus 600. And this should be a negative number, like this ln of 0.25, so that we get a positive time. Can someone calculate this number for us?
Minus 1.38.
Which one? This one?
39.
39? This ln or everything?
Yes.
Only ln.
Okay, can you also divide it by 600? So that we can find the time instant?
Minus 2.31.
What, seconds? It can't be because
Over,
this is 600.
over 1,000.
Over 1,000?
Yeah.
If it's over 1,000, then I will just say this is milliseconds, right?
Yeah.
Okay, so
It
can
should
you,
be
no,
positive.
this should be, yeah, this should be positive, exactly. Because this is negative, the result will be positive. Please double check this result. I don't have the complete solution here, so it's not easy for me to check, but I just believe in those numbers. Please double check, and then let me see the part C of this question. Alperen says, I agree, and then Emrah says, I think the same result. Okay, I think we found the correct result. And then,
Yeah, there's no issue.
Okay, perfect. And then part C says, let's focus on part C. Part C says, what is the power on 2 power of t, let's say, on this 2 millihenry inductor? So basically, we need to calculate the power here. Again, it's extremely simple for us now. We will just multiply voltage equation with the current equation. We have the current equation. We have the voltage equation. We have everything. It will be very simple for us. So let's say power on this 2 millihenry component is just V times R. And then again, I can just say, what information we have? We have IG directly. I can just use it. And then what else we have? We have voltage. We calculated the voltage, right? Yep, that should be very easy. So this is the voltage equation. But, well, someone should remind me the solution. Or, let me see if I can do this.
at the top now, voltage equation.
No, like when I go here, I should remember that equation. So this is, I will say, just paste if I can do this easily. This was our voltage equation, right? I just copied and pasted, and then our current equation is 5 times a lot of things. So 5 times e to the 200, 5 times e to the 800. So I just need to remember it. 5 times e to the minus 200t minus 5 times e to the minus 800t. Can you double check? I don't want to make a mistake here. And then I just go ahead and do the rest of the calculations. I will just do the multiplication. So that will be minus 10 times e to the minus 400t plus 10 times e to the minus 1000t, I believe. And then plus 40 times e to the minus 1000t minus 40 times e to the minus 1600t, hopefully. And then what I can do, so these are the same thing. So this will be just 50 times e to the minus 1000t, right? I don't know if there is any further simplification I can make. So that will be just the power here will be minus 10 times e to the minus 400t plus 50 times e to the minus 1000t minus 40 times e to the minus 1600t, and the unit will be here again, watts, and this is valid after t is equal to 0. So this is our power equation. We all agree with this? Do you all agree with this?
Yes.
Yes.
Okay.
In previous
So-
step, sorry. In previous
Sorry,
step,
can you say again?
in previous step, minus 40 times e to the minus 1600t. It's wrong.
Which one? This one? This
uh,
one?
I can't see. So, yes, e to the minus
Please.
16,000t.
1000? Okay. Wait a second. So you're saying no. Wait a second. Like we are multiplying this term with this term, right? So 8 times minus 5 is minus 40. And then both have powers minus 800 and minus 800. I just
sorry,
sum them up.
My mistake. Sorry.
Okay, perfect. Okay, no problem. Okay, now since we agreed, I will be continuing on this one. So the next part of this question says, calculate the time instant. So let's try to write it here. Calculate the time instant, calculate T star again. I will just say T bar, just to simplify, for maximum power. For maximum power. So so now we have the previous case that we skipped last time. So now we have the power equation. We need to calculate the time instant when we have the maximum power on this inductor. So how do we do this now? We already gave the answer before.
Take the first derivative, find the point at 0, and then check if it's a maximum or a minimum.
Perfect. So this is exactly the steps we should take. So we will just take the derivative of this P we calculated before, and then we will equate it to 0. We may have multiple solutions. We will check if they are maximums, minimums, and we will pick the maximum one, and we will say, okay, that time instant is when you have the maximum power, right? So let's take the derivative as fast as we can. So dp over dt is, now let's take the derivative. So that will be plus 4,000, I believe. right? And then the next one will be minus 50,000 times e to the minus 1000t, and then plus 64,000, right? E to the minus t, and then we will equate this to 0. Okay, so since we are equating to 0, I will try to find some common terms that I can play with. So what common terms I can factor out? So for example, I can directly get rid of this term by extracting this term from the other guys. So I will just say maybe 4,000 times e to the minus 400t. In parentheses, I will be having 1. Oops. 1. So for this one, if you divide 50,000 with 4,000, you will be having 12.5, I think, right? And then if I subtract minus 400 here, so that will be just minus 600. And then for this one, if you divide this with 4,000, you should be having 16,000. No, just 16, right? We agree with this? Please double check these calculations. This should be now 1200. Is this clear for everyone? So I just factored out this 4,000 times e to the minus 400t out, so that I now have a multiplication, because I'm trying to equate this thing to 0. It will be difficult to solve this problem by directly trying to solve this thing. That is very difficult. Is this okay for everyone? This current step?
Yes.
Okay. Can you use a calculator instead? Yes, exactly, Aaron. We can use a calculator at some point. Maybe this is a nice point, but we need to simplify these things a little bit more so that it's meaningful to use a calculator. So otherwise, you will be getting a lot of roots that we don't even understand. So here, if you look at this multiplication, this part can never be 0, right? Unless you are going to infinity, right? In a finite time, this thing cannot be 0, this left one. So if this equation is 0, that 0 will be due to this term. So this term should be equal to 0 at some finite t numbers, right? So here, just for simplification, I will say, for example, let x be e to the minus 600t, so that I can simplify this equation further. So in this case, I will be saying 1 minus 12.5x plus 16 times, like, since this is square of this term, so that will be x squared equals to 0. I think now it's a good time to use a calculator. So Aaron, did you calculate this? Did you find the roots? Okay, Aaron says something. Give me a second. So Aaron says t, one possible t, he says, is 4.8 seconds. Can you double check these results? How did you find this? Or wait a second. Did you mean this for x or t? Okay, I need a volunteer. Fatih Çelik says a different number. Okay, everyone says different numbers. Actually, we should be having 2 solutions here. Okay, what is that? Etembura writes 0.69 and 0.09. Are those for x or t?
X.
Okay. Okay, let me write these so that we can move on. So for x, you say one possible solution is 0.09, and then the other possible solution is 0.69. Okay, so this is our x. So what is t in this case? So that t will be, should be ln of that number, right, divided by 600, minus 600. So ln of 0.09 divided by minus 600, and then T2 should be, based on this calculation, T2 should be ln of this number divided by minus 600. And now I need these numbers, T1 and T2. Can you calculate these, T1 and T2?
T1 is 4 millisecond.
4 milliseconds.
Yes.
Okay, T2? Someone says something. T1 is
680 microseconds.
618 microseconds. Wait a second. I will just say US, like that U is micro. Or I can just say micro S. Okay, so these are two time instants where this power equation, the derivative of this power will be 0. But in order to know which one is minimum, which one is maximum, we should put those numbers back into this equation and calculate the power, right? So we have one more step. So let's take this equation. And again, I will need your calculations. So let's copy this. So now, please use your calculators and tell me what P1 is, what P2 is. So let's say P at T1, and then we will have P at T2, and then we will compare. Is there anyone who can calculate them, or are you calculating? I don't know. Are you calculating this, or should I do this? Okay, can you hear me?
Yeah, I'm calculating.
Okay, okay. Also, if any other person is calculating, please write the results to chat for PT1 and PT2 so that we compare them and decide which one is max. Anyone else?
For PT1,
Okay.
minus 1.17.
What?
Yes. In one.
Okay. So definitely that is the minimum. I mean, at least we have zero energy at t is equal to 0. So this T2 should be the correct case, but did you also calculate power at T2?
It's 4.3 watts.
4.3 watts, thank you. So as you can clearly see now, we can say maximum power occurs at T equals 618 microseconds, right? So this is the time. Thank you everyone for helping. Let's see the next problem here. So it says, what is the maximum power on the inductor, which is already calculated. Okay, so the response to that next one is this, like we know the maximum power occurs in this time instant, and basically maximum of P 2 millihenries will be 4.3 watts, right? Okay, that is already done. The next says, okay, this is nice. What is the T when energy is maximum? Okay, this is very nice. And then it also asks for the maximum energy, so we need to calculate both. So we will be calculating the time instant when the energy is maximum, right? So if you remember, I don't know if we calculated the energy before. Did we calculate the energy? No. Okay, we will do it now. So, so we all remember what the energy calculation was for an inductor. We were saying the energy is 1/2 times L times I squared, right? So in order to find the maximum, we will take the derivative of this with respect to 0, and then we will find the time instance, and then we will calculate this this thing. But we can make some intuitional comments here. First of all, so we will be, let's say we will be taking the derivative of this and equate to 0. So this will be a T star here. But actually, it is the case. So this is 1/2 times Li squared. This is equal to the time instant when you have di/dt is equal to 0, right? So it's like when you have the maximum current, you will have the maximum energy. Is this okay for everyone? Is this clear? Like, we are trying to calculate the time instant when we have the maximum energy. And I am saying, based on this equation here we have the maximum energy when we have the maximum current, because this is just a constant. So whenever this thing becomes maximum, we have the maximum energy. So I can just, instead of taking the derivative of that huge equation, which includes I can just take the derivative of this I and calculate calculate its calculate when its derivative will be equal to 0, right? Is this okay for everyone? This is really important.
It's clear to me.
Okay, perfect. So when do you get this thing equal to 0 then? So the next question is, can we try to intuitionally understand what happens when di/dt is 0? So if you remember the voltage equation, voltage is L times di/dt, right? So we are looking for the instant when this thing is equal to 0. Basically, we are looking for T star when voltage is equal to 0. Right? So if you follow the steps carefully, we are trying to find when energy is maximum, which is when the current is maximum. In order to find when the current is maximum, we will take its derivative and equate it to 0. But when derivative of current is 0, we know it is the time when the voltage is 0. And if you remember, just going back somewhere, I think here, we already calculated this time instant. So we know when voltage is 0. It is at T star equal 2.331 milliseconds. So I can immediately say this T star here is same as the one we calculated in part B. And I think the only purpose of this question, like, we did those steps, so now we are building on those solutions. So this is when T star is 2.31 milliseconds. Now, for the last part, I need to calculate the energy in this time instant. So that will be 331 times 10 to the minus 3, right? So I need to calculate 1/2 times, what was L, our inductance?
2 millihenries.
Okay, 2 millihenries. So this will be 2 to the minus 3 and then I will be calculating the I square. So I to 10 to the minus 3, so I will be taking the square root of this, right? So that will be my answer. And we need to do this calculation. So we have the current equation. I can directly put this number back into that equation, right? So we have the current equation somewhere. Maybe, okay, like far at the beginning. So is there any volunteer to calculate this? So we need to use 231 times 10 to the minus 3 instead of this t and calculate the current value here. This is the last thing we will be doing for today. So if you can finish this, we will be having all like numerical solutions for everything we did today. By the way, is there anyone who is calculating, or should I calculate?
I'm calculating the current.
Perfect, thank you. So if you can give us the number, then we will also calculate the energy after this step, so that these 2's will cancel. So this will be 10 to the minus 3 times the square of that current, whatever we get from, I think it was calculating.
Yeah, it's 2.36 amps. So squaring that, it would be 5.58 amps squared. And it's going to be, with 10 over minus 3, it's going to be millijoules.
Okay, 558 you said? This
Yes.
will be millijoules. Okay, perfect. Thank you very much. So this is our result here. So our result. Okay, so now we also calculated the energy. So it's like for this type of questions, we are trying to calculate almost everything. Like we are solving almost all possible questions, like energies, maximum, the times when you have the maximum energy, time when you have the maximum power. So all those things are like all summed up together. So that is a very nice question that I would really suggest you to work on this one more time, just to do the calculations yourself so that you can practice this again and again. So we can say, now this is okay for everyone in this class. Like you all understood this, this very well. Okay, let me stop recording.
The recording has stopped.
Okay, I think this is a good time to stop.